next is self-inductance of a long solenoid. So now we have to calculate what is the self-inductance of a long solenoid. If you know that the long solenoid or the solenoid basically consists of your coil, yeah, so obviously which consists of n number of turns, yeah, and again so which is connected across some external supply. Let's say this is the switch. Okay, so that is how it works, and definitely when you just close this switch, the current is going to flow, and the magnetic field along the axis of your solenoid is nothing but B is equals to mu 0 n into I. So this solenoid, again, it acts as a obviously bar magnet, but at the same time we can control the value of your that magnetic field either by changing the number of turns per unit length, either by changing the magnitude of current. Yeah, so that's why it is called a very that important application of your solenoids that you will find in various industries, factories, everywhere. Now again, the most important thing, what is the self-inductance of a long solenoid? Now that we have to calculate over here. So there are n number of turns over here. So the magnetic field along the axis, now that I have calculated. So what is the flux? So phi is equals to, we know that, so which is B into A. So the flux associated with one of the, let's say, turn, so this is B mu 0 Ni into A. So that is the value of your flux that we know. Now the next thing, at the same time that we can calculate, so what is the total flux? So the total flux, so that means obviously n number of turns per unit, you can say length. So the total flux, yeah, so the total flux generally we used to write down, so that is phi. Again, so over here that is a NBA, that is what we call as a number of turns. Yeah, so capital N is the number of turns. So the total flux, so you can say that phi t over here. So that is how we are going to write it down. So the flux because of one turn, mu 0 Ni A. Now at the same time we can just calculate again what is the number of turns. Yeah, so this is number of turns per unit length. Yeah, so that is number of turns per unit length multiply by that L. Okay, so that is simple how you will get the value of your total flux over here. So that is the total flux associated with this your n number of coils. So then we know that, so phi is equals to Li. So this is phi is equals to Li. So this phi t, let's say, upon I is equals to L. Then further I can write it down, so mu 0 n I, again I can say, let's say, n square I A. Yeah, again this is L. Further again I can write it down, that is your I, and this is your L. So I get cancelled, mu 0 n square, again A L. Okay, so now again I can say, so this is the value of your self-inductance, so that we have calculated for this particular case. Now instead of that n square, again you can just write it down. So this is that number of turns obviously, so this small n number of turns per unit length, so capital N number of turns, and again total length. So in that also you can write it down, that value. Now in this case, even that small n that we have defined, the number of turns per unit length, so that is also you can write it down, so which is n square A upon L. Again that is length of conductor over here, so that will be L square is equals to L. Yeah, so this is how you can write it down. One of the L get cancelled over here, and that will be your final expression, then mu 0 n square A upon L. Fine, so that is how we can just simplify further. So you can just cancel that one of L over here. Yeah, and then this is your again the final answer. So that is for your self-inductance of a long solenoid.